So, welcome to this course about how to use Rust for numerical computing on CPU for now. We will see next week how we can use it for GPU too using Vulkan. If you go to the Rust courses Discord channel and very soon to the calendar of the school, you will find the link to the official material. It starts with some introduction. There is an environment setup guide. Some of you may have followed it already, others will discover it today, that's fine. As you will see, there are several installation options because experience shows that different people have different preferences. Satellite sites prefer containers. Some people prefer local installs on their computer. Some people prefer containers. I don't want to force a choice on people, so I just have a guide for everything. Once you have done this general environment setup, you have a bit of course-specific setup, which is in the On Training Day page. The reason why this is a distinct thing is that it allows me as a teacher to update the source code that we'll be using without forcing you to download the entire environment again, because anytime people download containers, you know, the internet connection of lab may die, so that's not so nice. And once you have done that, again, please tell me if you run into any problem with these steps. You can get started with the course proper. A bit of introduction here. So, one difficult part of doing this sort of course is that it has multiple audiences. Some of you have some existing Rust background, or maybe, I don't know, web development, crypto, whatever, and they want to know how they can use it for floating point number crunching, which is one thing. Other people among you have more of a background in C, C++, Fortran, and they want to study the Rust option and see what it's like. Do they like it or not? And as you can imagine, this audience has quite different needs. And some of you are also a bit new to both. Sorry, people, this will be the hardest for you. I can try to be clear to everyone, but at some point you will have more new concepts and it will be harder. So how do I handle that as a teacher? Like many other teachers at the school, I cheat by providing course material that's usable for self-study. Most of this course, you could do it without me in the room. It's nicer if I'm in the room. I can answer questions, I can help you. But it's meant to be self-contained, something you can just follow on your own later. What this means is you can go at your own pace. If you see something you already know, you can scroll quickly, go to the next step. If you see something which is new to you, you can spend more time on it. And I will only introduce occasional synchronization points where I will quickly go through each part orally, rephrasing what's written in a more concise way, and explaining exercises in case people do not understand them or whatever. Speaking of exercises, one frequent feedback to previous editions of this course is that I should have corrections to all the exercises. You asked, I delivered. There are no corrections for all exercises in the form of a branch on the course Git repository. You can, if you know Git, clone the repository and view the history using your favorite history viewer. If I am just speaking Chinese to you, you can also follow this link in the intro, which will take you to the web interface of GitLab, which allows you to explore this history without knowing about Git. Like here, you see that this is the main branch, which is where what you're starting from. And then I have put on it a bunch of commits, which are changes, which represent the solution to each exercise in a sequence. And by clicking the little red dot next to each step, you can see how I change the code to fulfill this particular exercise. And again, I have those for almost everything. There is one exception, which is some exercises, but that's more in the GPU part, will be more open-ended in nature. I will be like, okay, you have studied 10 different ways to optimize this, try one and see what happens. Then, I cannot provide 10 corrections because that becomes impossible to maintain on the teacher side. So I will only help you interactively. You tell me, I'm running into issues with this exercise, and I will explain you then. Are there any questions about this so far? If not, I propose that you just get started. We have only one day for both numerical computing and Rust. It's short. Let's make the most of it. And yeah, again, the whole added value of having a teacher is that you can ask questions. So please ask plenty of questions. I love questions. And I just put some sound on my computer so that I can get Discord notifications to know when people ask questions in writing. This may result in a few undesirable notifications. Sorry about that. Maybe another little thing. I know that some of you have followed the course that I gave in November last year with NCC Slovakia. This is basically an updated version of this course. So if you understood everything then, there will be a few new things, but you can skip through most things quickly, and you will notice when there's something new, hopefully. If you did not understood everything at the time, which I suspect will be the case because, again, there's a lot of info, now is the time to understand it. Second chance. So yeah, as Pierre mentioned, for those who like to use containers, there are two variants. One is called Rust Code Server. The idea is to get a full IDE-like experience where you have an automatically set up VS Code in your browser with syntax highlighting that actually works, Rust Analyzer that automatically inserts your imports, all the cool things. And the problem is that, unfortunately, this won't work on every machine because containers are a problem. So that's why we provide a second image, which is a bit more minimalistic in nature, called Rust Lite, which contains just the minimum needed to build and run code. And then, editing code is something you do on your machine with your local tools. It's a bit less integrated, but it's easier to get working in some peculiar system environments, especially those that use Aptainer.
Just have a question. So I just tried to compile the first example, and I wanted to know what is the meaning of using cargo to compile the file, because I saw that you are compiling like lot of dependencies.
Okay.
And so I wanted to understand that instead of just using like Rust C to compile the file.
All right. So cargo is a layer on top of Rust C that adds dependency management and build orchestration. So if you come from a C and C++ background, you can think of it as the combination of make and CMake. And also maybe SPAC as well, because it can also download the dependencies for you, which CMake, well, yeah. People use it for that. I wish they stopped, because it's really bad at it. Now, why so many dependencies? Because basically, the way things are set up, all the binaries in this course share the same set of dependencies. This means that your first build will be unnecessarily slow. On the other hand, all subsequent ones will use the same binaries and should just be faster. That's the trade-off. If I wanted to have less of the upfront compilation overhead, then what I would have done would be to cut what we have in multiple cargo packages, and then I could have some more gradual dependency introduction. Speaking of which, so we're about half an hour in. If I did my homework correctly when writing my setup guide, normally everyone who's trying to get an environment set up should have one that's working now. If there's anyone who still struggles with environment setup, please tell me where you are and why it fails. Thank you. This will serve as input when I write the next version of the setup instructions so that you don't run into problem next time. Yeah, so sorry about that, Theo. Basically, Pierre had put the link to the old version of the course, and we only noticed yesterday, so there was a bit of misunderstanding here. It's now corrected. We should have the right link anywhere. If you find any link that has Grayscott with Rust in it, please report it and we'll make it disappear. In the loop exercise, I guess that's Jose. Sorry if I mispronounce your name. In the looping exercise, basically, if you are completely new to Rust and you follow this course, at this point, you do not have yet all the tools you need to do this using only iterators. That's why I have written this exercise in such a way that people who don't yet have the right primitive can still get it done, and then we see how it can be done better in the next chapter. I suspect that I actually cheated in the correction and used stuff that I had not introduced yet at this point of the course. But we need to check at some point.
Why there is an exclamation point after functions like print or debug?
So I briefly mentioned this in the first chapter, but I can explain it already right now. That's because these are not actually functions in a classical sense. These are macros. There's a few reasons why they have to be macros. Debug needs to know the current source location. This is something a function doesn't know. So it has to be a macro for this reason. Print needs to be a macro in order to accept a variable number of arguments, which is not a built-in feature of Rust functions. The Rust macro system in general is extremely powerful. Sometimes people are overusing it a bit, in my opinion. For debug, I think it's fair to say that the macro is the right tool for this job. For print, we could debate this. Right, as mentioned, fortunately, sometimes I need to move forward. Again, as the course is written, you should have the time to get back to it, and after the course, try to look into it again. It's also okay if you want to spend more time on a certain part while I move forward. In my opinion, when learning, quality is more important than quantity. Yes?
On the division from 1 to 1/3, why is there 4 in the digits?
Why is there?
Of 4.
4.
I have like 7, 3, 1, 4, and 2, 3.
Let me check. That's not it. So we are exercise first one.
Yeah, first one, yeah.
So which part are you talking about?
When I printed.
When you print it with 10 precision digits, that's because I lied. You cannot print a single precision floating point number with 10 significant digits. It only has 7 about decimal digits. The idea was just to remind you of this basic fact. You fell for it.
Thanks.
New question. So, yes, there's I'm sorry, I will not try to pronounce your name. I'm too afraid of doing something terrible to it. I am doing a Rust for the first time. There are a couple of questions. First of all, does the : symbol has similar meaning as in C++, like std cout? Yes. In both languages, this symbol is used to represent nested scopes of names. What C++ calls namespaces is replaced in Rust with another system called modules, which I will only briefly get into because I don't have enough time. And if you are accessing a method of a class, for example, a struct, as in C++, you will also need to use a type name : method. So that's a scoping operator. So, I see that if I do I8 max dot wrapping add 1, it works. However, wrapping add I8 max 1 throws error. Do all Rust functions behave like this? Yes, indeed. So wrapping add is what's called a method. It's a function that's attached to a type. When you define such a function, it allows you later to take a value of this type, tap a dot after it, and put the name of the function, and this will call the appropriate method of a type with the initial value as the parameter. You can do what you have in mind, but you must write it differently because there is no wrapping add function at the top level scope. It's a function of the 8-bit integer type. So in this case, you need to write and that will work. Scope is very important. It's what distinguishes well-behaved languages from Julia. When you have no scoping, it means that sooner or later, when you put two unrelated libraries together, you will have functions with the same name which don't do the same thing, which is a major software engineering sin. Rust does not encourage this, so it has quite a bit of scoping naturally. Another Discord thing that sounds Romeo specific. So it looks like they are fixing it on their side. Perfect. Good morning, Leanne, as well. And now I will move to some live explanation. Quick tip. If you are like me, Mike, please. If you are like me, and you don't like to have stuff on the sidebar when you don't need the sidebar right now, the user interface of the docs allows you to hide it with this so-called hamburger menu. As for why 3 horizontal dashes mean menu, you will have to ask a modern UI designer. It's just the way it is. Sorry. Everyone has agreed on it. It's a shame. So first chapter, and actually the most difficult chapter to write for a programming language teacher because you never know which order you should introduce concepts. There is one thing which everyone agrees on, which is that your first program, if you're in C++, should be a 1,000-line meta program that eventually prints an error message containing the hello world sentence. Beyond that, you're on your own. So in Rust, the hello world looks like this. So we define a main function. Function definitions start with fn in Rust, which for French people has unfortunate consonances, but that's okay, we can live with it. It's called main, that's a convention. Everyone agrees on this one. And it takes no parameter. Was someone talking? Okay, perfect. It may or may not return a result to indicate whether the program succeeded or failed. If you return no result, it means the program always succeeds. Then you have these curly braces, which are used to introduce scope. In this case, the scope is the set of instructions that will execute when you call this function. And after that, you have this thing, println hello world. So you will notice that this exclamation mark is a bit unusual by programming language standards. Like, why can't we, just call functions normally by just putting a parenthesis after the name without the exclamation mark? And actually, I gave it away a bit earlier when someone asked. That's because it's not a function, it's a macro. And the reason it's a macro is that, as we are going to see later in this chapter, it allows us to do things that require macro superpowers. Actually, thinking about it now, there are some things it can do that it can only do because it's a macro, but we'll also get into that. Next common topic in programming language courses, variables. And here we start to get a bit something that's more Rust specific. In many ways, Rust is a hybrid between programming languages from two different families. One is the C and C++ family, and the other is the ML family, such as OCaml or Haskell. And here we see actually this in action, because we have main function, stuff that sounds like C, but when we declare variables, we don't put types. We use a keyword called let, and we let the compiler infer the type of the variable that we have just declared. The ML family of languages was designed by mathematicians. Mathematicians get very upset when you tell them that you have a variable and now you modify it. So by default, variables are in Rust as in ML immutable. You cannot change their value after the fact. If you want to be able to do this, then you need to say so by using a second keyword, which is called mute. That's, if you know C, the reverse of the C convention, where you need to type an extra keyword to be immutable, which means that people will never do it. That's why it's important in programming language design to have the right defaults. If you want people to do something, make it the easiest thing to do. One polemical feature of the ML family, which Rust also inherits, is that it's very liberal about shadowing variables. The idea is that when you have a variable with a certain name, you can declare another variable with the same name, and it will effectively override the previous variable. And anytime after this line, if I refer to foo, I will refer to foo the string and not foo the integer. People have very heated debates all the time about whether this is a good idea or not. I will explain both sides of the argument. One side of the argument is that this is dangerous because you have one name which means two different things. The other side of the argument is that this is very convenient when you do things like parsing, where before you had some kind of string, you turn it into a number, for example, and from now on you only want to refer to this particular number. So the way shadowing is idiomatically used in Rust is when you have something that has the same logical content as a previous variable, but processed in some way into something with a different type. Second new thing, if you are coming from C especially, and C++ to some degree, is type inference. In Rust, inside of functions, we, by convention, almost never specify the type of variables. By default, the compiler deduces it from the context. This may remind you of the auto keyword that was introduced by C++11. But it's a bit more powerful than auto. Because auto does deduction in one direction only. It takes the value on the right-hand side. If it knows the type of this value, then it deduces the type of the variable. Whereas in Rust, we also have a forward operation. If at this point where I declare some variable, the type is unknown, but later I do some operation that forces a certain type, this will also be taken into account by type inference. Which means that there are less cases where we need to explicitly specify types in Rust than in C++, particularly when generics get involved. So 3 type inference cases in the Hindley-Milner algorithm, because that's the mathematical fancy name. First case, the value on the right-hand side has an unambiguous type. Here I put a string literal. The type for that in Rust is reference to string, which is written like that for short. Can you see the hybridization with C already? Then the compiler doesn't need extra info. It has a type on the right-hand side, it can use it. Second case, as I mentioned, I have a variable that's an integer, which is ambiguous, and then I use it as the length of an array. The length of an array in Rust is always usize, which is the local equivalent of size t in C. So, by way of conclusion, the compiler knows that this integer must be of usize type. And so it deduces. Third case, if all of the above has failed, there is a fallback, which is to imitate typed literals in C, which I find kind of unfortunate, but I know where it's coming from. So if we have no other information, we assume that integers are 32-bit signed integers, and floating point numbers are double precision floating point numbers. And the reason why the compiler does so is that it allows one-liners like this to compile. Otherwise, the compiler would tell you, I have an integer, I don't know what type it is, help me. There are some situations, however, where even with a more clever type inference algorithm, type inference will fail anyway. And this typically happens when you do not provide enough information in your code for the compiler to deduce the type. So here I am declaring an empty vector, which is a dynamically sized array to which you can add elements. I can do it in two different ways, but the problem is it's empty. And because it's empty, the compiler doesn't know, is it a vector of integers, strings, floating point numbers? Doesn't know. The problem is this must not be allowed because the properties of the resulting object will depend on the underlying type. For example, whether you are allowed to create a copy of this vector depends on whether you are allowed to create a copy of the contents. So the ability to copy is inherited from the element type. If you don't know the element type, you don't know whether you can copy it or not. And that's true of many other type properties. That's why when it reaches this kind of ambiguities, the compiler stops and says, I don't know, give me some extra info. You have two ways of doing so. The first way is you can use the type abstraction syntax. So after putting your variable name in the let statement, you can put a colon followed by a type. When you do that, you say, this variable will be of type, in this case, vector of bool. So it will be a vector of bool. You told the compiler, it's happy. Second case, you can say that you are calling the new method of vector of bool with this strange syntax, which is called the turbofish and serves to disambiguate syntax ambiguities between generics and the inferior, superior symbol. Unfortunately, we still have not learned about parsing ambiguities since people design C++, which is a shame. But at least it's familiar. The important thing if you want to write Rust and collaborate with other people is if you come from a language where types are often explicitly specified, this type inference may sound very weird and magical to you. And you may be afraid to use it. You may have, this instinct to put types everywhere. Please don't do this. Your code will be, to people who are used to normal Rust code, unnecessarily verbose. You don't need to do this because the type inference rules are simpler than those in C++, which means it's easier by looking at the code to guess what the types are involved. And the second reason you don't need to do this is that in Rust, unlike in C++, we have IDE support that actually works, which means that you can very easily install in your text editor a plugin called Rust Analyzer, and then you can easily highlight a variable and say what's the type of that, and it will tell you. So, combination of three things. It's weird to other people. It's less hard to guess the type if you try. And if you don't manage, a tool can do it for you. So please let types be infer. There is one exception to this, which is language enforced, which is that in Rust, unlike in other languages from the ML family, we don't infer types in function signatures and other kinds of globally visible objects. The reason why that is the case is that as soon as you have a function, a global variable, the type of this thing becomes part of your API, if it's a library. If you change it, you are potentially breaking users of your code. And in languages where everything is inferred, it's very easy to accidentally change the type in an API, as users of Python will know, even if it's dynamic typing versus type inference, which is a little bit different. So basically, don't put types inside of your function, but put them on anything that could become a public interface one day. If you don't, the compiler will yell at you. Now let's go back to this println. So it's a macro. And earlier I actually said something wrong. I said it's a macro because it needs to take multiple arguments. That was true 5 years ago. It's not true anymore because format strings have gained a new feature, which is that they can interpolate variables like f strings in Python. If you can interpolate variable, it means you can access variables from the outer scope. That's not something functions can do. So as with its current feature set, println can only exist as a macro. It could not ever become a function again if you wanted to, without losing features. This sort of thing is very convenient. It allows you not to use as often this style that is more common in C with printf. Because if you've ever used printf on a larger program, you know that it's a pain to figure out which argument maps into which particular placeholder in your format string. Another reason why this is a macro actually, so that had to be a macro even earlier than I thought, is that it's able to check that the number of arguments is correct at compile time, which is also something that variadic functions cannot do unless the compiler does some magic. It means it's capable of parsing the format string at compile time and telling if it's right or not. And that's a macro superpower. That's not something like a regular function can do at compile time. Finally, we have named arguments. So in addition to interpolating variables from the outer scope, you can also declare on the fly some values that are only valid in the context of this print statement. And these don't have to be, just variables. They can be expressions as complex as you like. And there's a whole domain-specific language for specifying how things are printed, kind of like printf in C again. For example, if you want to put a certain number of decimal digits after the comma in a floating point number, you have one syntax for that, which is, so you say, I'm printing x. This colon tells me anything after that is the end of the variable name and the start of the formatting the parameters. Then I use point, which is a formatting mini language for number of digits after the point. And then I put the number of digits. And if you want it to come from a variable and so on, it's possible as well. There's an entire documentation of everything you can do with it, which I link to. Println is not alone. It's part of a big family of functions that use the same syntax. Println stands for print line. It prints the string you stated, and then it adds a line field, which is often what you want when debugging. One cousin is called print, which doesn't have the line field. Another one is aprint, which instead of printing to stdout, which is the default, prints to stdr, standard error. And has a line feed cousin. They try to be consistent. Yet another cousin is write, which allows you to write to arbitrarily file descriptors. You can write to other pipes in your Unix process, files, network sockets, whatever. And format, which takes what you specified and produces a string out of it that you can keep for later use. And they all use the same syntax. For a reason that I will later get into, we actually have two different ways to print values in Rust with println. One which is called display and one which is called debug. What's the difference here? Display is meant for user consumption. It's something you would show to your user. You would there, print as an output to your program. Whereas debug is about stuff that you would type when you don't know why your program is not working and you just want maximal information. Because of this, they come with different guarantees. Display comes with some stability guarantee. People can expect that if they use the display method of printing, the output will stay the same when you update your library. With debug, there is no such guarantee, so you can go wild breaking everything as you need for debugging. And one important thing to realize is that some types do not implement display in the standard library, and there's a reason for that. And I will give the example of the VEC dynamic size array types that we've mentioned before. By the way, for people who know C++, it's a local cousin of std vector. It was basically the same. you may think that something like, bracket, set of items separated by commas, closing bracket would work. But my question to you is, what should happen now when your array has hundreds of thousands of elements? Should you spam your user's console with hundreds and thousands of lines of outputs, potentially producing an enormous program slowdown because you did not think about the length that the output could get to? Should you put ellipses, even if it means that users will not be able to know the elements in the middle when they use this method? There is no right answer here. And that's why there is no display. Display is supposed to be, the one true method for printing something. If you can think of a one true method, it should probably be a special purpose method of your type, not an implementation of the standard display operation. So here, example, I have a vector of stuff. It doesn't implement display. If I try to use this standard display syntax, it tells me nope. It tells me, because it's a helpful compiler, where it's coming from. And then I can go and learn a few things, like that I can use this. So this is a variation of what we used before. I put the colon again to separate the variable name, if any, from the formatting arguments. Here, there is no variable name because I'm using the comma syntax. And then I put a question mark, which means that now I want to go for debug formatting. I'm a developer. I know what I'm doing. Please print everything because I need to know everything. And there you go. It will print everything, as you asked. There are some interesting variations on this. Like, for example, strings by default are printed in the expected way. And in their debug representation, they have escaping, which means that you can copy and pass them into variable of your program easily as you would like. So here's an example of a string that contains quotes. And because I'm not using the raw string syntax, I need to escape these quotes. And here it tells me, OK, a string, if you put it in the display mode, you get unescaped quotes. And when there is a line feed, you get the line feed. If you go to debug mode, you get a starting quotes, escaping, and no line feed, which is much more convenient when you want to copy and paste it in your program again. So different use cases, different choices. There is another trick to the debug representation, which is the alternate debug representation. As you may guess, what I have been using so far, to print vector element by element is fine for small vectors. If it gets large or if the inner type is complex, it could get unwieldy. That's why we have the alternate debug representation, which looks like this. So now it puts one line per element, lots of line feeds, indentation. And that's very convenient when your value gets more complex and you can afford to print multiple lines, which is not always the case when you're doing things like logging. Finally, the ultimate printf debugging trick is the debug macro. It takes an expression as a parameter, and it will tell you several things. Why doesn't tell it here? Doesn't matter. I will do it my way then. What it should do, and it doesn't do here for some strange reason, and this is spoilers. Meanwhile, I can increase my font size a bit. So what debug tells you is a bunch of stuff, and I need to increase the font size anymore because there's so much stuff in here. That's useful. It tells you you are in a source file, which is a directory called examples, and which is called 01 let it be.rs. Inside this source file, you are on line 10 and colon 13, which allows you to locate the precise expression if there are multiple ones. You can also, with many text editors, pass this as a parameter to your text editor on the command line, and it will directly go to the right location. It says also, you try to compute this expression, unevaluated, and the result was this value. I guess you can imagine how convenient it is to have this for quick and dirty debugging. The potential is endless. Finally, the last tool that we introduced, because I also need it for exercises, is assertions. If you've been doing C before, you may have heard of the assert macro. You give it a Boolean expression. If the expression is true, nothing happens. If the Boolean expression is false, it may or may not abort your program depending on how it was built. Because that kind of behavior that changes depending on compiler configuration is not so in line with Rust design goal, the Rust assert does not work that way. Instead, if you type assert only, the behavior is the same in all program versions. Debug build, release build, it will always check. So that's good for fast checks, sanity checks that you can use to check, well, is my program doing something sensible or did something go really wrong, and is it better to crash right away than try to figure it out? For example, if you index an array at the wrong position, there's a bug in your code, you should not try to access that element anyway. You should just crash the program is wrong. And so here's an example. This will have no visible effect. It will do the check passes, it does nothing. This will say nope. 2 is not equal to 3, sorry. So you get thread panicked at this source location. Again, you can copy and paste this to open your text editor at the right location. Assertion failed, so you get the unevaluated Boolean expression, and you know that it's actually false, even if you expected it to be true. And if you set an environment variable in the right way, you can see how you got there in your program, which is also very helpful, much more so than C++ expressions when you need to fire up GDB to find out. And C assertions, which do not provide this option easily. Still, there's a reason why in C assertions have different behavior in debug and release build. Sometimes you have a check, which is too expensive to do all the time. But when you're debugging, you want to do it anyway because it can get you to the bug quicker. So sometimes you want the C behavior, and you can have it. It's just called differently. It's no debug assert. Second thing, unlike with C-style assertions, Rust assertions do not abort the program. By default, at least, they clean it up. If you have open files, remaining data will be flushed, files will be closed. If you have open network connections, they will be closed properly instead of making the server timeout and so on. Unlike unhandled C++ expressions, I mentioned backtraces come for free, which is very nice. And finally, you get formatting. So remember the println macro earlier. Here, if I have an assertion that fails, I can say, look, compiler, when it fails, I want you to print this format string with these arguments. It works like everything I mentioned earlier about println. And then, you get, if the virtual machine will dare to work, this error message, which can be more helpful than the original expression. You can also print extra detail here about the surrounding environment. If you know that just the expression alone, knowing that it's false, it's not helpful. You want to know what was the context in which it was evaluated, you can using this feature. There is one last trick for assert, which is specialized assertions. So far, all assertions I have been showing take a Boolean as a parameter and check if it's true or false. In the standard library, you have a few more special assertions, and in third-party libraries, you can have many more. One of them is assert ec. It checks if two expressions are equal. And if not, it will print you both sides, which is much more helpful than this is not equal. So you asserted that left is equal to right. You're a liar. Left is 4, right is 5. Go and fix your program. And again, you can customize your message as you like. So I actually did the live coding of the solution, and you have it in the branch. So since it's a bit late, I will not go further in this. Are there any questions on this? David closing pause.
Sorry.
Romeo fixing their stuff. Perfect.
Sorry.
Yes?
I have a question about my installation, if you can
Okay, perfect.
come.
Alors ça, c'est pas moi, c'est ton... Deactivate.
Ouais, mais du coup, je dois le run à chaque fois que je lance un
tu as dû mettre ton hrc ou ton .profile ou ton .bash profile.
Okay.
Il faudrait regarder les différents fichiers qui sont sourcés par le shell. Si ça le fait à chaque nouveau shell, c'est hrc, je pense. Sauf si tu es le genre de tordu qui met ça dans l'équivalent global de hrc, mais il ne faut pas faire ça. If not, we'll go for a break for now. And then I will take you a bit further in the interest of moving the course forward. I wanted to spend time on this first chapter because it's what everyone else builds upon. If you didn't understand this part, you cannot do any exercise, and that's bad. So I would say then, coffee time. We get back online around 11.